Graphs have many features. One of the most important ones is a gradient. We're going to look at examples where the gradient represents something meaningful. The first example we have here is a displacement time graph for a car that's moving, and there's some air resistance as well. What does a gradient of the graph represent? So first of all, you can see the gradient is changing. So we need to pick the gradient at a particular point. So you draw a tangent at that point, and then you ask yourself, if gradient is changing y, we're changing x, what does the change in y-axis mean? So in this case, there's a change in displacement, and the x-axis is change in time. So what is change in displacement over change in time? So hopefully you know the definition of velocity, that the rate of change of displacement is velocity. Okay, so therefore the gradient is velocity. The second example, we've got a velocity time graph, and we want to figure out what the gradient represents. So gradient is changing y over change in x, so we've got change in velocity over change in time. So change in velocity over change in time is the rate of change of velocity, which is the acceleration. So the gradient here represents the acceleration. There's another way of arriving at this. Given that this object is actually accelerating at a constant rate, because you can see the velocity increasing steadily, we can use SUVATs. So if I rearrange the SUVAT into the form y equals mx plus c, so I'm going to write y equals mx plus c directly below and compare it, because I've got y and the y-axis have got velocity and the x-axis have got time. The thing that's multiplying the x-axis, or in this case time, is the acceleration. So that is the gradient in this case. The graph below shows how the length of a spring changes as a load is added to it. What does the gradient of the graph represent? So gradient is change in y over change in x. So in this case, change in y is change in force, and change in x is change in length here. And if you look through equation sheets under the materials topic, you'll find change in force over change in length, or extension, is equal to spring constant. That's Hooke's law, or it's also known as stiffness constant. And now we've got a stress strain graph for wire that's stretched. What does the gradient represent? Okay, so gradient here is going to be change in stress. As you don't need the change in this example, so stress over strain, and that's the definition of Young's modulus in the materials topic. The graph below gives the resistance of a wire against length. Determine what the gradient represents. Okay, so I could do change in resistance over change in length, but if you look through equations, you're not going to really find an equation for that with the change there. So we're going to try a different approach. We're going to go through the equation, and under the electricity topic, and you find this equation here. We've got resistance and it's got length as well, but it's also got resistivity and area as well. Then you're going to compare it to y equals mx plus c, because it is a straight line and you can do that. So on the y-axis we've got resistance, on the x-axis we've got length. So it's a bit easier to see if I separate out like this. So you can see the thing that's multiplying the length, or the x-axis, is resistivity over area. So that is your gradient, resistivity over area. The sixth example here, the graph below shows gravitational potential varying with distance from the center of the planet. What does the gradient of the graph represent? So let's look through the equation sheet again. So change in y is change in potential over change in distance here, change in r, radius. And if you look through the equation sheet, you do find an equation like this, but it's got a minus in front of it, and it represents a gravitational field strength. So if you want to find the gravitational field strength, you have to find the gradient at a particular point and multiply by -1 in order to get the gravitational field strength. Now we've got electric potential against distance. Okay, same approach. Change in V is going to be the change in potential, and against change in distance, like so. And if you look through the equation sheet, you get E, capital E here, which is electric field strength. The graph below shows a variation of magnetic flux density through a coil of wire. The area A and the number of turns of the coil N is fixed. Explain how the maximum EMF can be determined. Okay, so I suspect it's the gradient of this graph, so I'm going to check what change in y over change in x is. So change in magnetic flux density over change in time. Now I'm going to look through the equation sheet and look for equations which might have these. Unfortunately, there's no equation which has this directly, but there is one that is quite linked. Okay, so that's for EMF, which is what we're trying to find, and this is Faraday's law. So rate of change of magnetic flux linkage with a negative in front of it. And if you dig a bit deeper, that magnetic flux linkage is B times A, magnetic flux, which is B times A. So I've put that into the equation like so. Because the area is a constant, it's not changing, I can take that out of the delta. So rearrange this slightly a bit more so it makes a bit more sense. I've got change in magnetic flux density over change in time, which is the gradient of this graph. So one thing I'll have to do is I'll have to figure out the gradient of this graph and multiply by the area and the number of turns, the -1, to get the maximum EMF. And I had to pick the steepest part to get the maximum EMF, because you can see the EMF is proportional to the gradient of this graph. Final example, the graph below shows how the temperature T of an object changes as it's heated. Energy E is supplied at a constant rate. What does the gradient represent? Okay, the gradient is going to be changing y over changing x. Let's pick a point where there is a change in y, which is a change in temperature, and there's a change in energy there. Okay, so I'm going to look through my equation sheet under the thermal physics topic for an equation, and the one that's closest is this one here for specific heat capacity. And I'm going to try to get delta T over delta E in that equation by rearranging things. So I'll bring the delta E to the bottom on the right hand side and the MC to the other side. So I'll bring like this and so. So that tells us the gradient of this graph is equal to 1 over the mass times the specific capacity, which is represented by C in this example.